Alright, Chapter 2, Radical Functions. So this is a little bit of a repeat of what we've already done. We've already looked at transformations of all sorts of different graphs, but now we're going to specifically look at just radical graphs. So those are our roots. So we're going to start off with square roots and kind of see when we apply the transformations what happens to them. So then that means we need to go back to our function notation. So we have our four variables being used, a, b, h, and k. So our a value, that's our vertical stretch. Our vertical translation is our k value. Both of these affect our y, or our height of our graph. Our b value and our h value, those both affect our x values. So our b is our horizontal stretch. But remember, x is always do the opposite of what you want. So this is actually the reciprocation, so it becomes 1 over b. Our h value is our horizontal translation. So even though it says minus h here, this is actually a positive h if it was to say a minus here. So just remember those two things and you should be all right. Moving on. So from previous knowledge, let's graph f of x equals square root of x using a table of values. Now that might be how you'd graph something in grade 8 or 9 or 10. Now when I'm square rooting something, I can't square root a negative. So right away I have to pick values of x that are greater than or equal to 0. Next, if I'm going to graph something, it'd be nice if I could actually plot it somewhere and know what the answer actually is. So I'm going to pick perfect squares. So for instance, we have 0, 1, 4, and 9. So square root of 0 is 0, square root of 1 is 1, square root of 4 is 2, and square root of 9 is 3. So we're going to plot these points. So we have 0, 0, 1, 1, 4, 2, and 9, 3. Now, radicals are continuous graphs, so we should connect this dots and actually put an arrow to say, hey, this is going on forever. Here, our first example is graph using transformations first, then confirm using a table of values. Now, I have over here vertical stretch, vertical translation, horizontal stretch, horizontal translation. It might be helpful for you to actually identify what is what to start. Some of you might want to use mapping notation as well. So for our vertical stretch, it comes from our a value, so it's 2, and then our vertical translation is -4. So again, these are both our y values. So I would apply those transformations first in one step. So I'm actually going to redraw the parent function. So 1, 1, 4, 2, and 9, 3. So just quickly, you're going to have to memorize that quickly. And we should actually label what this is. This is y square root of x. Next, vertical stretch. So I'm going to multiply each height by 2 and then subtract 4. So 2 times 0 is 0, minus 4 is -4. 2 times 1 is 2, minus 4 is -2. And then 2 times 2 is 4, minus 4 is 0. 2 times 3 is 6, minus 4 is 2. So again, connect the dots. And we should label this. This is not fully complete. This is actually just the a value of 2 and then the vertical translation of -4. So we have one more translation left to do. We have this -2, but that's actually a +2. So our horizontal translation of +2, meaning I'm going to take each of these points and shift them 2 to the right. So this point will go here, here, shift right 2, shift right 2. Oh, this is a little bit off the graph. So then we can go and graph our final. And so that's going to be, again, labeling it 2 square root x minus 2 minus 4. We're almost done. It does say to confirm using a table of values. Now, probably the easiest way to do this is to actually pick the points that we have currently. So here my x value is 2, so I'm going to use that value and substitute in, so 2 minus 2 minus 4. See what that equals? It equals -4. And check, does that match? Yes, perfect. Next, we have a point at x equals 3. So substitute in 3 for my x value, and we get -2. Does that match? Yes, perfect. Okay, let's do one more. We have x is 6. So 2 times square root of 6 minus 2 minus 4. is 0. Does it match? Yes, perfect. We're done. Finally, we have example 2, graph lists what transformations are occurring. So I go to actually do, I've got something different here. I've got a reflection actually. So a vertical stretch of 1, but we actually have a reflection with that at the same time. And that's actually it for our y value. It's just reflected. Oh, sorry, no it's not. We've got a -2 here, a vertical stretch of -2. So I'm going to go and graph my parent function. So 0, 0, 1, 1, 4, 2, and 9, 3. Again, we should label that y equals square root of x. And now I can go and graph this. So I'm going to multiply each point by -1 and then subtract 2. Well, 0 times -1 is 0, -2. And then 1 times -1 is -1, -2 gets me -3. 1 times 2 is -2. And then we have -2 more yet. And then finally, 3 times -1 is -3, -2, so we get to -5. So now we can connect this for our continuous graph. So this is the graph y equals negative square root of x minus 2. All right, let's take a look at our b value. Right away, actually, we have a problem here. The 3 hasn't been factored out. So we actually need to rewrite this equation as negative square root of 3, and then 6 divided by 3 is 2. Now all of the y value stuff all stays the same, so we don't have to worry about changing anything else. So that means my horizontal stretch, well, it'd be tempting to put that it's 3. It's actually 1/3. It's the reciprocation. And then I have a shift of -2, and that's actually 2 left. So again, remembering that is opposite. So I'm going to take each of my points, my x values, divide them by 3, and then shift them 2 left. So we'll start here, 0 divided by 3 is 0, and then 2 left, so 1, 2. And then this point, 1 divided by 3 is 1/3, and then shift over 2 left. And then 4 divided by 3 is 1.3, and then 2 left, so 1, 2. And finally, 9 divided by 3 is 3, and then divided by shift left 2. So there's our graph. It's going to look something like that. And then we're going to get y equals negative square root 3x plus 2 minus 2.